Welcome to Clean Tech Deep Dive. In our last episode, we touched on two water-related topics.
We did.
Today, we're taking a deep dive into something incredibly important: advanced and sustainable wastewater treatment technologies. You've shared a really comprehensive collection of articles and reports with us on this.
Yes, quite a stack.
And our goal here is, well, to distill it all down. We want to pull out the most crucial and frankly, fascinating insights so you can grasp this vital field without feeling, totally overwhelmed.
Sounds like a good plan. It's definitely a complex area, but super important.
Okay, let's get started.
Right. So it's clear from the material you sent over that there's been a real evolution in how we think about wastewater treatment.
And evolution, yeah.
What's fascinating is that it's no longer just about removing the stuff you can see.
Right.
Modern treatment is really fundamental now, protecting our rivers, oceans, wildlife.
And our own health, too, right?
Absolutely, our own well-being. It goes way beyond those traditional settling ponds and basic filters that just focused on visible contaminants.
Exactly. It's like we've realized that what we can't see can often be the most harmful. Things like pharmaceuticals, microplastics, those persistent organic compounds.
Mm-hmm. The really tricky stuff.
Traditional methods often just aren't equipped to handle them, and that's where these advanced technologies really come in. Your sources strongly emphasize that clean water isn't just nice to have.
No, it's presented as a fundamental human right.
Yeah. And these advanced treatments are key to actually achieving that.
Absolutely.
Yeah.
And as we dig into these advanced technologies, a few core methods pop up again and again in the sources.
Okay.
One that's particularly interesting is zeoturb. One article described it as a liquid bioorganic polymer.
Bioorganic.
Yeah, and it essentially acts like a magnet for suspended solids and turbidity. It just pulls those tiny particles out of the water.
A magnet for muck.
I like that visual.
So it grabs the minuscule bits that make water cloudy.
Precisely. And what's key here is that being bioorganic, it lowers the environmental impact compared to older chemical coagulants. That's a big step for sustainability, especially with water scarcity being such a challenge.
Makes sense. Okay, we also saw a lot about reactive catalyst technology. That sounds like it really kicks things up a notch.
It does. Think of it as something that dramatically speeds up the breakdown of pollutants right down at the molecular level.
Ah,
The whole idea is to make the treatment process much faster and more efficient. One source even pointed out that using it with something like zeoturb can seriously boost effectiveness.
how so?
Well, you're not just removing the particles, you're also breaking down the dissolved contaminants much quicker.
Ah, I see. So they work together. Then the magnet grabs the solids and the catalyst speeds up, breaking down the rest.
Exactly. Synergistically.
That makes perfect sense.
Hmm.
But what other key tools are in this advanced toolkit?
Yeah.
Electrocoagulation was mentioned quite a bit.
Yes, electrocoagulation, that's a really intriguing one. It uses electricity to treat contaminants. Electricity, not chemicals.
Right, that's the key difference. It's a significant shift away from chemical-heavy methods.
Yeah.
Basically, an electrical current goes through the water,
Okay.
and it causes the pollutants to clump together,
Mhm.
making them easier to separate out, so you minimize the need for adding harsh chemicals.
That sounds much better for the environment. And then there's enzyme treatment that feels more natural, like tapping into nature's own processes.
Precisely. Enzymes are biological catalysts. They naturally break down organic matter in wastewater.
So a gentler approach.
Generally, yes. Compared to some chemical methods, it lets natural processes happen, just, well, controlled and sped up. Now, shifting gears slightly, another major category that got a lot of attention is membrane filtration.
Ah, yes, the high-tech sieves. Ultrafiltration, that term came up a lot.
It did, and ultrafiltration, it truly is like a superfine sieve. It catches incredibly small particles. We're talking 0.0001 to zero point 0.1 micrometers.
Ah, that's tiny.
Tiny enough to effectively remove bacteria and even viruses. So it's critical for things like drinking water purification. Makes sense.
And also in industries like dairy and pharmaceuticals where you need really high purity, the specific size range is important. It means you can get rid of harmful microbes, sometimes without needing chemical disinfectants.
Okay, so that's the go-to for the really small biological nasties. And then we have microfiltration. Sounds like it operates on a slightly larger scale.
Exactly. Microfiltration works on particles in the 0.1 to 10 micrometer range. Think of it as ultrafiltration's counterpart for slightly bigger stuff.
Like what?
Well, it's used in sewage treatment to filter out microorganisms, clarifying beverages, even in dairy processing, often without needing chemical additives. So bigger particles than UF, but still playing a vital role.
Okay, so we've got physical removal with membranes, chemical or electrical methods. Now, advanced oxidation processes, AOPs, those sound like the big guns. For the really stubborn pollutants, right?
They certainly are. AOPs are really a group of powerful techniques. They use strong oxidants like hydroxyl radicals.
Hydroxyl.
Yeah, very reactive. They break down those really persistent pollutants, the ones that just don't degrade easily with other methods.
Okay.
One of the sources mentioned GenClean liquid AOP technology. It's an example of a catalyst that actually generates these reactive oxygen compounds internally right there in the water,
Oh, interesting.
which makes it highly effective for both contaminant removal and disinfection. It's like they create their own cleaning power on the spot to hit those tough substances.
That's pretty ingenious.
Yeah.
Now, another key disinfection method we saw highlighted was UV light. I know they use that in some home water purifiers.
They do, and it's quite effective on a larger scale, too. UV light at a specific wavelength around 254 nanometers works by directly damaging the DNA or RNA of microorganisms.
So it stops them reproducing.
Essentially, yes.
Yeah.
It prevents them from functioning or reproducing, basically neutralizing them. And the benefits are significant. Well, no chemicals added. It's highly efficient against a wide range of pathogens, and it's considered very eco-friendly. Research mentioned in the article strongly backs this up. That specific wavelength is key. It packs the most punch for disrupting microbial DNA without leaving nasty byproducts.
Right. No chemical residue is a huge plus. But
Yeah.
I recall reading that some things are more resistant to UV.
That's a very important point. Yes. Some microorganisms, like adenoviruses, for example, can be more resistant to UV disinfection.
So what do you do then?
That's where those advanced oxidation processes, the AOPs we just talked about, can be particularly valuable. They often prove effective even against these UV-resistant pathogens. It adds another layer of safety.
Okay, so it's often a combined strategy. Makes sense.
Yeah.
Now, the sources also spent a good amount of time on where this is all heading, the emerging trends in sustainable wastewater management. It's clearly about more than just cleaning the water itself, isn't it?
Absolutely. The focus is really shifting towards managing wastewater in a way that's not just effective, but truly sustainable and resource conscious. Well, non-potable water reuse is a major trend. There's a big push to treat wastewater so it can be safely used for things like irrigation, industrial cooling systems,
Oh, the flushing even.
toilet flushing, exactly. Things that don't require drinking water quality. This helps conserve our precious potable water supplies.
Giving water a second life for less demanding jobs, that's really smart resource management. And I saw a mention of solar-powered treatment plants. That sounds amazing.
Yeah, minimizing the environmental footprint even further. And speaking of resources, it's not just about the water itself. What's in the wastewater?
You mean besides the contaminants?
Right. Wastewater actually contains valuable nutrients, like nitrogen and phosphorus.
From agricultural runoff and sewage.
Often, yes.
Yeah.
And there's a growing and really important trend towards nutrient recovery, using techniques like anaerobic digestion, struvite precipitation, ionic exchange,
Okay.
to actually extract these nutrients. This does two things: reduces pollution in waterways and decreases our reliance on synthetic fertilizers. So you're helping sustainable agriculture.
Turning pollutants into fertilizer. That's pretty cool.
It really is, turning potential waste into a valuable resource.
So we're not just cleaning up waste, we're extracting value.
Hmm.
That's a fantastic example of a circular economy. And it doesn't stop at nutrients, does it? I remember reading about recovering other things too.
Precisely. Metal and resource recovery is another key trend. Things like copper, zinc, valuable metals can be recovered from certain wastewater streams using selective recovery methods, various eco-technologies. Again, it supports that circular economy idea by reducing the need to mine new virgin resources.
Like urban mining almost, mining our wastewater.
In a way, yeah. So looking ahead, what are some of the major challenges and future directions? The sources touched on several key areas.
Yeah, what's coming down the pipe, so to speak.
Well, one significant challenge highlighted was hospital wastewater, especially post-COVID.
Yeah, more volume, different contaminants.
Both. Increased volume and a really complex mix of contaminants, pathogens, pharmaceutical residues, disinfectants. It's tough stuff.
So what's the solution there?
AOPs, those advanced oxidation processes, are seen as very promising for tackling these complex challenges. But the articles also stressed the need for evolving regulations and, importantly, public acceptance around treating and potentially reusing this water.
Right, public perception is always key. Okay, hospital wastewater is a specific challenge. What about broader trends? I recall one article looking specifically at the U.S. market out to 2030.
That report pointed to several big shifts. Stricter EPA regulations, especially around things like PFAS, lead, nitrates, are expected to really drive the adoption of more advanced treatment tech.
So regulation pushing innovation.
Exactly. The report anticipates widespread adoption of membrane filtration, reverse osmosis, ultrafiltration, plus advanced multi-stage filtration and AOPs. Desalination is also expected to grow, particularly in water-scarce regions.
Okay, more advanced tech becoming standard. What else?
Sustainability and water reuse, for both industrial and agricultural use, were seen as huge drivers, fueled by both technology and regulation. Also, modernizing aging water infrastructure, hopefully with some federal funding support, was a key prediction.
Our pipes definitely need an upgrade.
They do. And finally, the report noted the growing role of public-private partnerships for funding and managing these bigger, more complex projects.
Okay, so significant investment and upgrades needed. But are there potential roadblocks? Challenges foreseen?
Yes, definitely. The report mentioned ongoing issues with emerging contaminants, think microplastics, endocrine disruptors.
Stuff we're still learning how to deal with.
Exactly. They'll require new, innovative treatment approaches. And another big one, cybersecurity. As these systems get more digital and interconnected,
They become targets.
they become potential targets, yes.
Yeah.
Protecting water treatment facilities from cyber risks is a growing concern.
Definitely crucial. Okay, beyond that specific U.S. report, what other future trends did the materials point towards?
We saw several really interesting ones gaining momentum. Smart water management is a big one.
Using IoT, AI.
Exactly. IoT sensors, artificial intelligence, big data analytics for real-time monitoring, predictive maintenance, fixing problems before they happen, and just optimizing how everything runs to cut down water waste.
Makes sense. More data, better decisions.
And also decentralized treatment systems, smaller, localized facilities. They're gaining popularity, especially for areas without big centralized infrastructure, or maybe for specific industrial sites.
Good for remote areas, maybe.
Yeah, or for providing more tailored treatment locally. Another huge focus is energy efficiency and resource recovery.
Using less power.
Right. More high-efficiency pumps, better membrane designs to reduce energy use. Plus, really doubling down on recovering those nutrients, biogas for energy, and the water itself.
Closing the loop.
And alongside that, more sustainable and green technologies generally. Things like constructed wetlands, green infrastructure, using renewable energy to power the plants.
So a real push to minimize the whole environmental footprint. What about some of the more cutting-edge stuff, maybe not widely used yet?
Yeah, some exciting developments there too. Electrochemical treatment, using electricity more directly for removing contaminants, potentially cutting down on chemical use.
Interesting.
Nanotechnology, developing new nanomaterials, carbon nanotubes, graphene for potentially much better filtration, absorption, or catalytic processes.
Wow.
Also, innovations in biological treatment engineering, specific microbes or microbial communities to break down really complex pollutants more effectively.
Tailor-made microbes.
Kind of, yeah. Bioaugmentation and solar-powered water treatment is definitely one to watch, especially for off-grid applications. Forward osmosis was mentioned to potentially less energy-intensive than reverse osmosis for desalination, though still mostly in R&D. And modular portable systems for emergencies or remote sites.
It really sounds like a dynamic and rapidly evolving field, which must mean, for anyone listening who might be thinking about careers,
Yeah.
sounds like opportunities there.
Absolutely. The sources touched on that. A diverse range of paths in environmental engineering, water treatment. You could be a water quality analyst, a treatment plant engineer, a sustainability consultant.
Lots of options.
Yeah, it's definitely a field where you can make a tangible, meaningful contribution to a sustainable future.
Well, this has been a truly fascinating deep dive into the complex world of advanced and sustainable wastewater treatment.
It really is complex, but so vital.
It's clear it's multifaceted. There's this impressive array of technologies, evolving trends. It just underscores the crucial role this whole sector plays in securing a sustainable water future for everyone. What were some of the key, moments for you wading through all this? How does it connect to the bigger picture of water scarcity and environmental protection?
That's a good question. For me, I think one of the biggest aha moments is just how interconnected everything is becoming. It's not just about cleaning water in isolation anymore. It's integrating resource recovery, energy efficiency, ecological thinking right into the core of wastewater management. It really drives home that tackling water scarcity isn't just about finding new water sources. It's about managing the water we already have much, much smarter, with a real commitment to sustainability.
Smarter management, not just more water.
Exactly. And seeing how advanced tech is converging with a deeper understanding of ecosystems, that's actually really inspiring. It offers some real hope, I think.
Definitely some important points to mull over. Before we sign off, don't forget to check out the description section. You'll find key highlights from each episode to help you dive a little deeper. Thank you for tuning in to Clean Tech Deep Dive.